In this video, we'll be talking about thermodynamic processes. We'll take a look at how much work can be produced by a piston inside of a Nerf gun, and we'll conclude with thermodynamic cycles. To start out, we'll take a look at thermodynamic processes. So, thermodynamic process. Thermodynamic process takes a system, which we defined in the first video, as some area that we want to analyze. So, it takes a system from one state to another, and a state is just some moment in time described by thermodynamic properties. So we can use a useful tool to represent different states, and it's in the form of a graph. So we'll have a vertical axis and a horizontal axis, and what we do is put a thermodynamic property on the horizontal and vertical axis. So on the horizontal axis we'll put volume, and the vertical axis we'll go ahead and put pressure. And when we have a point on this graph, this point represents a single state. So this specific state has a volume, and we'll just call this the initial state. So this state has this volume, this initial volume, and it has this initial pressure. If we have some other state, so this is also a state. This state, we'll pretend like this is our final state, so this will have a final volume and a final pressure. And because the process takes our system from one state to another, if we draw this represents the process. And the line itself represents the process path. And from this graph, one useful thing to look at is the area. And to determine what this area represents, we can look at the units. So vertical axis we have kilopascals, and the horizontal axis we have meters cubed. We know a kilopascal is a kilonewton over a meter squared. We still need to multiply by that cubed meter, and this gives us a meter on top, so kilonewton meter. And we know that a newton meter is a joule, so this gives us kilojoules. And joules is the unit of work, so we know that the integral of this curve, which is called a process path, inside of what's known as a PV diagram, or a pressure volume diagram, we know that this integral is equal to the integral starting from the initial volume to the final volume, the pressure times the change in volume. And although this curve is not linear, if we approximate this curve to make it linear so that we don't have to use any calculus, we can calculate the integral by first calculating the area of this triangle right here, and then we can add the area of this rectangle. So we'll go ahead and get started. The area of this triangle is going to be equal to 1/2 times the base, which is the initial volume minus the final volume, times the height, which is the final pressure minus the initial pressure. And then we want to add the area of the rectangle, which is just going to be the initial volume minus the final volume times the initial pressure. And there's these two common terms, so we can factor that out to get the initial volume minus the final volume. And then if we distribute this 1/2, we get 1/2 the final pressure minus 1/2 the initial pressure. And we need to add this initial pressure because this also gets factored out. And so we get, if we take out this process, so if we look at the initial volume minus final volume, and then we get 1/2 times the final pressure, and then we'll add half of the initial pressure, which gets us to VI minus VF times 1/2 times the final pressure plus the initial pressure. In the last video, we looked at the final and initial pressure and volume of the piston chamber inside of a Nerf gun. So I'm just going to copy down the values from our last video. So we had, oops, I think I pressed a random button, but no worries. Gave me enough time to find these values. So the initial volume was equal to 1.885 meters cubed. The final volume that we had in our last example was 1/8 of that, so it was 0.2356 meters cubed. And both of these need to be multiplied by 10 to the negative fifth. And then we had as our initial pressure the atmospheric pressure of 101.3 kilopascals. The final pressure as 810.41 kilopascals. And the last video goes into detail about how we calculated these, but we'll just say that these are given for now. These are given, and we'll use these values to calculate the amount of work that the piston does inside of the Nerf gun. So the work is going to be equal to, and we'll use this formula right here, the initial volume, so 1.885 minus the final volume, 0.2356, and we'll need to multiply by that 10 to the negative fifth meters cubed, and we'll multiply all of that with 1/2 times the final pressure of 810.41 plus the atmospheric pressure or the initial pressure of 101.3, is all in kilopascals. And so we get, pull out our handy calculator, 810.41 plus 101.3 divided by 2 times, in parentheses, 1.885 minus 0.2356, which gets us 751.89 about. So 751.9, we'll just say 751.9, and then we need to multiply that by 10 to the negative fifth, and this will be in kilojoules, which we found above. So this actually represents about 752 752 kilojoules, which is equal to 7.52 joules. So this is saying that the piston inside of the Nerf gun is doing 7.52 joules of work. Now, is this the actual amount of work that the gun is doing to the bullet? And one thing we have to consider that we didn't in this calculation above is the atmospheric pressure. Atmospheric pressure. I'll go ahead and pull in a diagram of the Nerf gun again so we can see why our calculation above wasn't actually quite right. So this is that Nerf gun again, made by Jerry and Ern, and we'll take a look at the pressure. So this piston is pushing to the left, and in the last video, remember I said those holes right here that interact with the bullet chamber right here that allows the compressed air to push the bullet out. So this bullet goes out because the piston compresses the air. Now the problem is that because there's a hole right here that interacts with the environment, there's actually also atmospheric pressure pushing against the piston. And we didn't consider this atmospheric pressure. So we have to readjust our calculation to get what's called the useful work. And the useful work essentially just takes into consideration the work done against the atmosphere. So we have that same initial volume minus final volume, And we also have still that final pressure plus initial pressure over 2, but we also need to subtract that atmospheric pressure. So now we're doing the calculations a little bit. We have this as equal to 1.885 minus 0.2356. That's all multiplied by 10 to the negative 5th meters cubed. And we have that 810.41 plus 101.3 all divided by 2 minus the atmospheric pressure. That's the new addition. And we find that this gives us, let's see, 1.885 minus 0.2356. So this gives us 1.6494. 1.6494 times 10 to the negative 5th. And then we'll take 810.41 plus 101.3. We'll divide that by 2 and subtract the 101.3, that new atmospheric pressure that we didn't previously consider. We get that 354, and we need to multiply that by 1.6494 times 1.6494 to give us 584.8. So this is equal to 584.8 times 10 to the negative 5th kilojoules, which is equal to 0.005848 kilojoules, which is equal to 5.848 joules. So this is the actual work that the piston does, the useful work that the piston does to accelerate that bullet. Cool. Now we'll move on to the thermodynamic cycle. So for a thermodynamic cycle, they are just processes. So it's a process with the same, what an E. Anyways, the same starting and ending state. And this is best represented using another specific type of diagram. So this diagram, instead of having volume and pressure, we'll keep that volume on the horizontal axis. This time we'll have temperature on the vertical axis. And this, remember, can be some state. So we can call this our initial state. So this has some volume, and we might have some other state that also has some sort of volume. And previously we had one single process, right? But a cycle is a process with the same starting and ending state. So we have to go back to this initial state. And again, this one was the process path. And we'll see cycles later on in the course quite a bit with some different engine analyses. So it gets pretty interesting. Thank you for joining me on this video. I'll see you in the next one.